emission standards. Okay. We did this one too. Oh yeah. Now I remember there was a video. It's 5 minutes long and I didn't want to hold you, but we'll go ahead and watch the video. So reasons for air quality improving it started long ago, 1970, with laws, and there's momentum for the public awareness of clean air and clean water. As equipment breaks down, the new technology is cleaner. And so this little video we'll talk about. And among them were ozone, which is O3, and particulate matter. 2.5 is worse than 10, isn't it? So these are showing you the number of unhealthy days per year in general. So Los Angeles, oops. Now, one of the things about ozone is it's a secondary pollutant. And so in order for it to be formed, it takes stuff that isn't dangerous and like volatile organic carbons, we're going to talk about those, and it makes them into ozone. So it needs sunlight to do that, was my point. And is there a lot of sunlight out there on the West Coast? Yeah. I say West Coast, but not so much in Seattle. Sunlight? Is it cloudy there? A lot more than... Yeah. So actually that can work for them with regard to sunlight not creating the ozone. So particulate matter, again, Seattle comes out pretty good. Let's see, who's bad with regard to particulate? Sacramento, Boston. Boston's on the high side for particulate matter. And if you look at the map of the United States, our East Coast, historically, that's where we landed first, and we got industry started there, and then we kind of migrated here. So, yeah, so we still have issues related to back to the 1800s out there. One of the things you mentioned, rain in Washington and stuff. One of the videos we watched showed Beijing, and it showed kind of before a rain event and after the rain event. And if your intuition is that the rain can kind of cleanse the air, your intuition is very correct. So, anyway. This actually, I'm going to take you to this website called Air Now. It's also referenced in our textbook. But this you can put in your zip code and get an air quality report. So red is bad, green is good. So Air Now. I checked it the other day and we're just fine. So Air Quality Index, AQI, I believe it kind of looks at certain markers, so not just one pollutant. It's thinking. Yep, so if we put us in, well, you could already kind of see by all the green. The green is good, and kind of the color is not. 52632. Oh, we don't have any air quality available. How about, let's take a quick look at Chicago. So these all look pretty good. How about Sacramento? California.
Why do you think over by like Omaha?
Omaha?
Yeah.
Actually, Chicago was.
Was what? I know. Like, cause it's kind of like, if you look at the map, like it's just out there in the middle by itself. Mm-hmm. Like, is there something?
I'm thinking urban, sort of the whole industry, and actually this is like, I don't know, when it was refreshed. So this is as of today. So we talked about temperature inversions. Temperatures or weather patterns can kind of play havoc. But
I didn't know if like there's something in that area. It's like nowhere, and like if you look at the big one, there's nothing anywhere near it.
Right.
It's yellow. It's like all green. Bam.
Right. Again, it's kind of like Wind patterns can, if the wind isn't,
The wind could be completely different in that.
yeah. Well, I
Like
do
you
think
just
the
said-
emissions. I think you're going to have more industry in a large city like that too. So, but it is kind of because you have other large cities,
I was
and
gonna say like Des Moines, Kansas City, like
what's that?
Is that a large city, Omaha?
Omaha.
I never.
I've been there. It's pretty big.
it's not as big as Chicago though. It's kind of
No.
That's right.
yeah, because like Chicago just has that itty bitty. You know, there's probably all the moisture there. You know, up by that. Like,
Yeah. Interesting. Let's take a look at California. What's that? Yeah, topography can definitely play havoc. Yeah, we've got a little more color here with regard to having issues. And we have the forecast here too. Right.
so green. Right?
Well, probably not. This is, yeah. This one actually broke it down. I picked on 129 that's for the particulate matter. This kind of breaks it down into the different things that are going on for that location.
Is it like hard to breathe whenever you're like in areas like that, like physically?
I think especially I've read if you have asthma, if you already have something, if you're already compromised in that way, it's hard to breathe. I think it's just hard to breathe otherwise.
I think it's harder to breathe anyway if you move like that way because my boyfriend's family always goes like Colorado and stuff because they have mining claims out there, and they say that every time they go out there they get sick because.
Yeah. Now that could be an elevation issue. Yeah. Yeah. So that's an issue, and then there's the smog, the particulate, and the ozone issue.
That's like unhealthy for sensitive groups.
Mm-hmm. I know sometimes, like, you'll be driving down the interstate and it'll have a sign that'll say ozone alert, and it's like, ooh, yuck! Don't get out of your cars.
Oh, it does say up there health message.
Yeah. Yep. It's interesting. This actually is a figure from your textbook that just has, for instance, picking on Phoenix in Arizona for yesterday, today, tomorrow, and the day after tomorrow. So of course the red hot is poor air quality, but like the caption says, it can be actually natural causes too. We have natural causes of pollution, such as forest fires and volcanic eruptions. So interesting. All right, on to part 4. We'll see how far we get. Dun, dun, dun. Finished it up about 9:30 last night. We've already been talking a little bit about chemical reactions. So. But this we talked the other day that chemists kind of look at chemistry kind of on the small scale. We can look at kind of the symbol of chemistry. What's C stand for? Carbon. Why is there a 2 there for the O? Because it's a diatomic element. Yeah. Remember there are 7 diatomic elements: copper, nickel. Oxygen's one of them. What's CO2 stand for? Carbon dioxide. Yep. So in general, when we burn something, we're taking, in this case, carbon. When we burn something, we're combining that something with oxygen. Carbon will form carbon dioxide. That's the symbolic.
What's the middle one?
Up here.
In the blue circle?
Oh, combustion. Now, this particulate is trying to show you a picture, and we're actually going to start talking quantities, like quantities and how many carbons. Well, we have one carbon atom, and it's joining with one O2 molecule to form one CO2. So that's the picture of that. My builds are off, aren't they? Okay. So the first word up here is reactants. The thing that we start with are reactants, and what do we end with? Products. Yep. So those first two words are reactants and products. Very good. And then what other word did I take out a word here?
It says must be equal.
Oh, equal. Equal's gone. Thank you. Each side of the arrow must be. So we're going to be looking at some pictures here. So what I say when I talk about this topic is this idea of I kind of put a brick wall here, and then I kind of have a tally, like I have carbons and oxygens on the reactant side, and carbons and oxygens on the product side, and they have to be equal. So here's my brick wall. Here's my carbons and oxygens. So I have one carbon here, and I have two oxygens here. I have one carbon here, and two oxygens here. That's what I mean by equal. Okay, they got to be equal. So in science, there's a lot of things that are conserved. In our world, there are a lot of things that are conserved. Basically, what you start with, atoms you start with have to be representing atoms that you end with. All right. So we're going to actually do this thing called balancing equations. And there are some hints here. The first hint is that if you have an element is present in just one compound, we're going to balance it first. First is the word there. Okay. So if you look on both sides, you're like, well, that element is in only one compound. We're going to balance it first. Then the next thing, the word is last. If you have anything that you're looking at your reactants or products, and you have something that is just what we call a free element, like O2 is a free element. Why? Because it doesn't have anything else with it. C is a free element. There wasn't anything with it. So leave those to last. And then the other thing, and I'm going to do an example, is if you have, and we haven't talked about this yet, what are the two types of compounds? We talked about that. Yep, ionic and molecular. Yep, exactly. So which one has a metal in it? Yep, ionic. It has metal. You got it. The other thing about ionic compounds is you're going to have starts with letter C. What do we call something if it's positively charged? We didn't talk about that yet? Cation? Yep. Oh, sorry. And an anion. Anyway, you'll have something that's positively charged and something that's negatively charged. That will give you an ionic compound. So there are these things called polyatomic ions. And so I brought a sheet that I use in my other classes to show you what polyatomic ions. Have you ever heard of nitrate before? It's a polyatomic ion. Nitrate looks like this. Has one nitrogen and 3 oxygens, and it runs around with a -1 charge. So it's stuck together. It stays as a unit. And so what this will hint for making sure your equations have the same number of things on either side of the arrow in your reactant product side, it says go ahead and keep those as a unit. And so I was like, well, how are they supposed to know what a unit is? And so this is kind of these are some common things like nitrate that are all stuck together. Okay? So this is just kind of a quick reference. So the way it's set up is if you find nitrogen, you should find nitrate. What else do you find for nitrogen? Nitrite and nitride. Yep. Exactly. While we're at it, since I just gave this to you, what I usually tell students is to add 2 if they didn't make it to the list. Because they're positively charged, add this one, if you would, NH4, and it has a +1 charge, and that is ammonium.
Where do we put that in?
Kind of in the spot. I would just put it kind of down here.
Like on its own.
Yeah, on its own. Yep. And that one's kind of common. It frustrates me a lot of things in how people name things frustrate me. You've probably heard of ammonia, right? Ammonia? Like liquid ammonia? But, excuse me, ammonia is only NH3 and it's not charged. Okay, so that's actually a compound and that is an ion. The other one, if you don't mind, and it's probably less likely that you're going to run into this, but it's Hg, and it's got, what element is Hg? Letter M. Mercury. Yep. So it's Hg2, 2+. And it actually is called mercury, Roman numeral 1. Mercury 1. That just is. Because actually each of those mercuries is a +1, so it's mercury 1. And that's they stick together. I was just thinking it, just kind of thinking out loud. It's gonna, like, your final is so far off in here, but even if you can't use your book, you're gonna have a periodic table. You'll have some reference things. So, all right.
There's gonna be a lot of this stuff on it.
No, because it won't be any of this stuff on it necessarily, unless we get to it in chemistry and context, because we haven't seen any of this. But this is just, this might help you in a minute. So the other thing is, remember a minute ago when I said carbons equals oxygens equals, and I did on either side, the reactant side, product side, you just need to do a double check to make sure that you have the right numbers in everything. Oh, both sides. Is that ordinary sides? And both sides. Right. All right. So here's an example where we're going to burn methane. So methane is going to react with oxygen on the reactant side, and it's going to form carbon dioxide and water. Now, if I draw a little mark here, here's my brick wall. I'm going to count carbons and hydrogens and oxygens on either side. I have 1 carbon, 4 hydrogens, 2 oxygens, 1 carbon, 1 carbon, 2 hydrogens, 3 oxygens on that side. Okay, so it's not equal right now. By the way, if you look at a chemical equation like this, and it just has the number 1 is implied there, even though there's no number, and it's the no number to the left, it's implied as 1. So we need to bump up our hydrogens, okay, on the product side, and we need to increase our oxygens on the reactant side. So in order to do that, look what my bills look like. Let me clear this off. In order to do that, well, I'll do it this way. If I go ahead and if I focus on my hydrogens, if I put a 2 here, it's a big 2 in front of H2O. That means I have 2 H2O units. Now, if I have 2 H2O units, I need to update my hydrogens and oxygens. How many hydrogens do I have if I have 2 H2O units? I update it to 4. Perfect. So how many oxygens do I now have? I have 2 plus 2. Yep. Oxygen's updated to 4. That's perfect. And to me, balancing kind of goes back and forth. So I put a 2 there. And now what's out of sync still? Your oxygens. So how can I get 4 oxygens on the reactant side? Put a 2 in front of the O2. That's it. That's totally it. Let's go ahead and update. And now my oxygens, instead of 2, there are 4. And so I've got equal on either side. That's it. That's how you balance it. So I need to do this. So this is what we did. We put 2, and I kind of went, I could have done it differently, but I went from the hydrogens first. I put a 2 there in front of my water, and then I fixed my oxygens on this side and put a 2 there. That's it. It's balanced. The word I think we're missing up there is unbalanced. Is the word missing? Unbalanced and balanced. Excellent. This is actually then what it would look like. This is carbons are black, hydrogens, these 4 hydrogens, so this is methane, CH4. This is O2, and we needed 2 of them. And here is the CO2. We only had 1 of them. And here is Mickey Mouse's our water. So those big numbers, we put the 2 in front of the H2O and the 2 in front of the O2. Those are called stoichiometric coefficients. Sometimes I call them coefficients, COEFF. Sometimes I call them stoic coefficients. Okay, but they are used to tell you how many of the reactants and products that you have involved. Oops, sorry, in front. I guess there's a word. Number in front of the chemical formula. So if you're balancing, sometimes students are tempted to go ahead and just change the subscripts. If you change the subscripts, you're altering the reactants and products. This changing the big number to the left is changing not changing what's used or formed, but changing how many. Okay, so let's take a look at this one. So I'm going to draw my brick wall, count my P's and my CL's, P's and my CL's. With coefficients of 1, looks like I got 4 here, I got 2 here. On the product side, I've got 1 phosphorus and 3 chlorines. So I'm going to go ahead and try to get my phosphoruses right. How can I get my phosphoruses right? Yep, put a 4 here, and then update my phosphoruses to 4, and then how many chlorines do I have? I have 12, yep. I have 4 PCl3 units, so for each PCl3, I have 3, and I have 4 of those, so 4 times 3. Yep, 12. Cool. Yep, so if I just put a 6 over here, and then update my Cl2s, that's it. Just 1. Okay, so let's balance these equations. So I'll give you a, well, we already did that one, didn't we? How about this one? This one we already did. Remember, we came up with a coefficient of 2 in front of the H2O and 2 in front of the O2. Now, so if you're okay, let's just skip to the other one. The sheet I gave you, if you look under sulfur, what is SO4? It is sulfate, yep. One of my things that just a burden to carry is there's also an SO3. What's the name of that? Sulfite, yeah. And I almost feel rude saying sulfate, sulfite. It just seems rude, but A and I mean 2 different things. But anyway, so when we balance this, I'm going to keep my SO4 together. Okay, can you find OH on there? On the sheet I gave you? Hydroxide, yep, I'm going to keep my OH together. Now you could break them out but do you see where I have like an SO4 unit here and an SO4 unit here? I have an OH unit here and OH unit here. I'm just going to keep them as a unit.
Why is that?
That means I have two of those. So when I tally them up, I'm going to show two. So here's my brick wall. I'm going to go with aluminum. I'm going to keep SO4 sulfate together. I'm going to go with sodium, and I'm going to go with OH. I'm going to do the same in that order on the product side. So aluminum, SO4, Na, and OH. So how many aluminums do we have starting out? 2. How many sulfates? 3. How many sodiums? 1. How many OHs? 1. How about the product side? Aluminums? 1. SO4s? 1. NAs? 2 OHs? 3. Cool. And I say I go get a cup of coffee because I'm like, well, you could begin different places. But let's go for our, and sometimes you need, it's called by trial and error, so we might have to revisit things. Let's fix our OHs first. That's okay. So how do we fix our OHs? We put a 3 over in front of NaOH. I'm going to put a 3 there, and I'm going to update. My NAs are now 3, and my OHs are now 3. That's cool. How can I fix my SO4s? I put a 3 over here. 3 on the product side. Because I had 3 over here. So now my NAs are, what, 6? Dang. And my SO4s gave me 3. Okay. So our aluminums are still messed up. Our sulfates work. Our sodiums are messed up, and our hydroxides work.
So SO4, what's that extra 3 behind it? So it's got
SO4 means that actually for this whole compound, the formula has 3 SO4 units.
okay.
Yeah. So for one formula unit, it has 2 aluminums and 3 SO4s. So this is a messy one. Let's go ahead, just for kicks, and fix our aluminums. I know it's also messy. Looks like we're going to have to erase something. So if we fix our aluminums, I can put a 2 over here. Does that seem right to fix my aluminums? So now if I do that, I'm going to update. My aluminum is now 2, and how many OHs do I have? I have 6. Yep. Oh, see, I just messed up something that wasn't broken. This will work though. What is still broken? Oh, the sodium hydroxides.
So the OH, the 3 for the NaOH should be a 6.
Yep. I like that. So what you're saying is if I cross this out and make this a 6, and now I update, things are going to fall into place. Yep.
There's no easier way to do this.
It's called trial and error. There's a mathematical way of doing it, but it confuses me even worse. This is called by inspection, back and forth, trial and error.
Oh, I learned it.
What's that?
I learned it.
Okay, your turn. Your turn. So I'll give you a little bit. See what you come up with.
I was thinking of it. Oh, I was looking at the bottom. Gosh, dude. Just kidding. Psych. I was seeing a beer. I was seeing a beer.
That's what you got. Some of them are easier than others. Oh, while I'm at it, and I'm not going to take it to the website, but I think I'll post it. There's like a calculator for anything online. There is, if you type in balancing equations, there is something out there. All you got to do is type in the unbalanced equation, and it will spit you back the balanced equation. I've used it before. So that's pretty fun. I think we're all good with that. Okay. So complete combustion means that CO2 is what the carbon turns into from the oxygen. And if you're burning an alkane, or hydrocarbon, the hydrogen in anything that you burn combines with oxygen. Of course, hydrogen plus oxygen is water. So on the product side, if it's complete combustion, all you're going to see are carbon dioxide and water. Now, if there's not enough, my word is not enough, there's not enough oxygen, and that could be for different reasons. If your car is like not tuned up as well as maybe it could be or should be, I don't know how cars work, but you don't get enough oxygen there for complete combustion. And so then on the product side, in addition to CO2, or instead of CO2, you're going to see CO. It makes sense. There's not enough oxygen, so instead of CO2, you only get CO. That's incomplete combustion. So this is complete combustion. Okay, notice the product, we have carbon dioxide and water. Wow, those are some big stoichiometric coefficients. This is octane, right? 2 octanes plus 25 O2s will give you 16 CO2s and 18 H2Os. If I were to look at the carbons and the hydrogens and the oxygens on either side, they would be the same. And this is incomplete combustion. So what's the difference between these two? There's two differences I see. What's that? There's not as much O2. Yep, this is less. And then what else? Yep. The CO versus CO2. And the way it works is, although carbon dioxide we're concerned about it in the atmosphere because it adds to, it makes our planet warmer. Carbon monoxide is a poison. Okay, so carbon dioxide is not a poison in itself, but carbon monoxide is. Okay, your turn. Go ahead and draw your brick wall. And these are balanced, so go ahead and convince yourselves that you have the same number of atoms of carbon, hydrogen, oxygen on both sides of the reaction, both of those. Feel free to pull out your calculator. So like for instance, so from this side we have 16 carbons, and 2 times 18, 36 hydrogens. Convince yourselves. Did you get the same on each side?
I think it's the 25, like the 50, 25 times 2. Right?
Yeah, so 25 times 2 is 50. And then over here you have to take 16 times 2 plus 18. So 16 plus 2 is 32 plus 18. 32 plus 18 brings you back up to 50. So I think. So I think that's a good place to leave it for today. So we didn't get through this, but we should have no problem doing part 4, and then part 5 is the last part in chapter 2 on Monday. So if you have any questions throughout, you can always email me if you have any questions, and you're like, I wonder what. Anyway, have a good weekend.